Hello, multivariable calculus students. This is Mr. Johnson, and this is the second video for section 11.1. And we're going to talk about level curves, which is just our second portion here. And level curves of a particular function is a way for us to get a sense of what the function or the surface is doing. So ultimately, what we're going to use these for is trying to figure out maybe a high point on the z-axis or a low point on the z-axis for a particular function. When we start to analyze maximums and minimums and those types of things, we're going to look at level curves for the overall behavior of a particular surface. The way that we do this is that we take a look at the equation for the surface. So let's say it's f of xy, and we let the surface equation equal a constant k. So in other words, what we're really doing here is we're just taking z, which is going to be the function value of xy, and we're letting z equal a number. So if we let z equal 5, for example, what is the equation then if we were to take z is equal to 5 and assume just that particular curve along that section of the surface? So I know this is really small, but in this picture here, you can see that z is 20 is going to be this particular curve in space right there. And so you project all of these down on the XY plane, and you take a look at then what the behavior is, maybe the spaces between the curves, possibly the actual curves themselves in terms of what their values are, and we get a sense of how steep the surface is or how quickly the surface is changing, or even just estimates as to what the surface may be in between the level curves. So for example, if we're looking at in between k is 25 and k is 20, for example, if we were to say, all right, I'm going to pick a point right here, and I'm going to project that up to my surface, you can actually estimate that, okay, that's probably going to give me a z value around 22, 23 possibly. And so through this process, through these level curves, we're able to analyze a surface a little more effectively, but at least just analyze it in a slightly different way. So here's a real simple graph of a bunch of level curves, and we can see the function values that are written in, and we're being asked to estimate two different values, f of 1, 3, and f of 4, 5. So let's take a look at f of 1, 3. We're going to look specifically at this point right here on our graph, and we can see that the level curves are between 70 and 80, and it looks like we're closer to 70 than 80. So I'm just going to say that this is approximately, and this is no exact science here. We're just, if you said it's 50, that's going to be way off. But I'm going to say it's approximately 72, maybe 73, somewhere in there, based on what I'm seeing from the graph. If we were to take a look at f of 4, 5, if 4, 5 is going to be here, and I can see that my level curve right here is actually 60 if I travel around and kind of trace that out. So that's going to be 60 and 50. So it's closer to 60 than it is 50 by a little bit. I'm going to say that's about 56, maybe 57, something like that. So we're using it as an estimation tool. If we kind of project this idea, we can see that this is going to be, either of these values are going to be probably high spots on the graph, just based on the behavior. We're going, 50, 60, 70, 80. And so it looks like maybe some maximums here. That's what we're going to start to study a little later in chapter 11. Looks like there's possibly a minimum down here and certainly low spots all along the edge because it's at 50, the smallest value, but there's also this low spot in the middle. So maybe some peaks in a valley there. Maybe, those are minimum, that minimum value, maybe there's some maximums there. But anyway, that's the type of thing we're going to start to analyze with these level curves. All right, let's take a look at sketching out these level curves. And I have some graphs included just to speed up the process a little bit. I've used Desmos to do this. So what I encourage you to do is utilize the Desmos app or just go on the Desmos website. It's a great tool and it just allows you to do this really quickly to get a sense of what's going on. One of the things that I want to mention though is that we want to think about in the past what we know about certain surfaces. So for example, if this was z equals 6 minus 3x minus 2y, if you were to rearrange this, don't forget what we've done in our previous chapters. This is a plane. And we can see that it's a plane with a normal vector of 3, 2, and 1. And so we know some of these surfaces. Other surfaces are going to be very bizarre to us just because it's a new process, but we've done some pretty distinct surfaces that we want to still be aware of. Now what we're going to do is we're going to let the z value equal 4 different k values. So remember what we're doing is we're letting z equal f of xy equal k, and we're going to graph a series of equations. So for example, if z was equal to -6, then I have the equation that looks something like that. And so for a moment, just think about your plane in space. And if you were to take and let z be a constant value, and you were to draw the level curve, it would be a line along that plane. And if you projected that line down on the xy plane, that's really what we're trying to do here. So algebraically, I'll just show you this one quickly. So you would subtract 6 and get -12. And let's go ahead and set this up so that we know the visual a little bit better. So we're going to add 2y, -3x plus 12. So that gives us the line y equals -3/2 x plus 6. So that would be the level curve if the function was equal to -6. So I'm going to move over here and show you all the level curves. So I just showed you the red one. So I set up and I allowed, again, over here in Desmos, I used K and K and K and K. So in other words, I on an XY plane, I showed you all of the level curves for those 4 values. And this is the one I just showed you algebraically. And you just do the same thing with the rest of them. And so, this gives us an idea of the surface we're dealing with. It's a pretty boring surface, just a plane, but the level curves show a linear pattern. And if we were to go take a look at the plane itself, here's the graph of the plane. So what we're doing was we're taking our k values and we're just allowing k to be, for example, -6, and we're drawing a line, and then 0 and drawing a line, and 6 and drawing a line. So we're getting these lines along the plane like this, and we're projecting them down onto the XY plane to get a sense of what's happening to all of these little constant values of z. Okay, so that's the level curve. Let's look at a slightly more interesting one. So we're going to take a look at, this was back in example 3. Okay, so you can make a note if you want. This is example number 3. And same equation, okay? However, we're going to look at the level curves, and I didn't really leave myself any space here at all. Let me just show you really quickly. Let's say that I'll go off to the side here. So we have g of xy is equal to the square root of 9 minus x squared minus y squared. Let's say that, and again, we're going to let this equal k. And the very first one there is k is 0. So let's just let this equal 0. And so algebraically, what you would get is 0 equals 9 minus x squared minus y squared. And x squared plus y squared is equal to 9. And we know what that looks like. It's going to be a circle with a radius of 3 centered at the origin. And so here are my level curves that I have through Desmos. So that very first one that you see, this one here, this red one, that's the one I just showed you. You could let k equal 1. It's going to be the blue one, k equal 2, k equal 3. That's the green and purple one. The purple one is, of course, just, I don't really have purple on my screen, but purple one's a dot. So it's going to just be a dot at the origin because k would be 3, and then that 9 would cancel, and we would just get 0. So anyway, you get the sense that, okay, there's this surface that has some level curves that are closer together on the outside, and then they get further and further apart. I mean, take a look at the green circle compared to the dot in the middle. That's really, really fast. And so you start to think about the surface itself. We studied this in example 3. We know it's the top hemisphere of a sphere. So when you think about a sphere, that makes a little bit of sense, is that there's a lot of change here on the outer edge of that sphere. I have the three-dimensional graph of this. There's a lot of change that happens early on, and those level curves are going to be really close together because there's drastic increase in this case. And then as you get up to the top or the upper portion of the sphere, there's a much more gradual increase or change in the z values, and those level curves are going to space out because of that. So those are some of the things we start to learn about when we look at the surfaces and the level curves that they form. Okay, let's look at the next page really quickly. So this next page is an activity that I typically do as a large class like this. And so what I would like you to do is just try this on your own. Use Desmos, play around with some of these surfaces. Let their values equal k. Just start to plug in some items for k and take a look at some of the level curves that exist. Another thing that I would suggest trying to use, because we don't have the Quick Graph Plus app right now on or the GeoGebra AR apps on the iPad, is that you can go into I don't know if this works on an iPad, but on a computer you can go into Safari and you can just type into Google, for example, don't use f of x, y, type in z equals x squared plus y squared, use z, and oftentimes Google will actually graph for you a three-dimensional object, and it's a pretty decent graph. So you can use that a little bit as well, but what you're trying to do is you're trying to map the level curves to the surfaces. And again, you can use Desmos for the level curves, that's totally fine. You can then use Google to try to figure out what that three-dimensional object will look like. Keep in mind that on the next page, I have the answers for you, and so you can check your work from there, but just try some of that on your own. All right, on to the next page. Hey, we have one more example, and this is a very abstract one. We have level surfaces rather than level curves. So we're going to primarily deal with level curves because we're dealing with three-dimensional space. But if you go into 4 dimensions, well, then it's no longer level curves, it's level surfaces, which is very abstract. So we have here f of x, y, z is equal to x squared plus y squared plus z squared. So if we were to come up with level surfaces and let this particular function be k, then we could, for example, let k equal 1, okay, and we have 1 equals x squared plus y squared plus z squared, and all of a sudden you can see over here in our picture that we have a sphere with a center at the origin and a radius of 1. Or for example, let's say we want to let k equal 4. Well, then we have 4 equals x squared plus y squared plus z squared, and of course that's over here. That is a sphere centered at the origin with a radius of 2. And so all of a sudden you have these level surfaces that dictate the 4-dimensional object, which we in fact cannot visualize because it's in 4 dimensions. So there is a little bit of an extension that occurs here. We're going to live in the world of 3 dimensions for the most part when it comes to level curves, level curves in order to analyze the surface itself rather than level surfaces. All right, that does it for us for section 11.1. Thank you.